right, ladies and gentlemen, today we are going to be talking a little bit about what are called limiting reagents or limiting reactants. We're also going to look at our Fuzzy Wuzzy Lab first aid. So please take out notes for limiting reactant. Fuzzy Wuzzy, we need about 40 minutes to do. Quick feedback I need. 5 means the stoichiometry is easy. 1 means I'm not sure what you just said. Anywhere in between, how you're feeling. There we go. 5, 4, 3, 2, 1, hands up. 5 is stoichiometry easy. 1 is I don't know what you just said. 2 is in between 3, 4, 5. Alright. Now, if your hand is up and you are showing a 1 like this, or a 1 with your middle finger, or a 0, I hope none of those are happening, but if you are, please come in during Wolverine time. Please come in during Wolverine time. Lunch, I sometimes am in here, and if you catch me at the beginning, I'll help you. If you catch me at the end, I won't. So, if you're here or here, I do need you to see me. We will be using that skill today. So the thing we're going to learn about today is what is called the limiting reactant. So here's our problem. This is an example of the limiting reactant problem. We've got 8 car bodies and 48 tires. The question is, how many cars can you make? Now a car is only a car if it has tires, just so you know. We're not talking about the ones that are parked out in front of your house. If you might be that type of person. So, 48 tires, 8 car bodies. What's the answer to this? 20. 8. Any other answer? How many cars can you make? 28. 28. Alright, so let's check this out. Here's our equation. We got a car, we got 4 tires, that makes a complete car. So car body, 4 tires makes a complete car. So the ratio is what to what? 1 to 4. That means if I got 8 car bodies times it by 4 used to equal 32. So I would need 32 tires. If that is correct, I should be able to make 8 cars. If you said 8, you are correct. Now, what's left over? Our tires are left over. You've got 16 tires excess. Okay? Does this type of problem make sense? Okay, this is using some basic stoichiometry, and usually the chances we have something left over. That's called excess. The probability of this happening in real life is almost 100%. It's like 99.99999%. You always have a little bit extra of one or the other. So what we're going to be referring to is the tires are excess. That means the car bodies are called the limiting reactant. Tires are excess, car bodies are limiting. Now, if we had more car bodies and less tires, or vice versa, could these two be switched? This could be the limiter and this could be excess? Absolutely. It all depends on how much you start with. So it's very easy to see this could apply to almost any situation. In chemistry, when it applies, you call that the limiter or limiting reactant and the excess reactant. The 8 cars here is what is called a theoretical yield. So in theory, according to our stoichiometric ratio of 1 to 4, we should get 8 cars. Now in reality, let's say these 48 cars, okay, half of them are flat, the tires. Then we got a problem, right? Maybe we could get 8 cars, but maybe the cars don't run so well. So that's a reality problem, but in theory, we're going to work with our theory first. That's called the theoretical yield. Reactant equals reagent. If you see the word reagent, it equals reactant. Limiting reagent is the same as the limiting reactant. And reactants are on what side of the equation? Left side of the equation. Products are on the right, of course. Yes, sir. Question? Okay, yield also is referring to a product. So if something is yielded, but that's what theoretical yield means. How much can be produced. Now, the limiting reactant is the reactant that is consumed first. It limits the amount of products formed. Sometimes people say it's used up first, consumed first, the one that runs out. Those are all ways of describing the limiting reagent, or limiting reactant, sorry. So before the reactant started, we've got a green one and a red one. The green is the limiter and the red is the excess. Why? If we look at what happens at the end, what is left over here? Red. All the rest of the greens are hooked up with a red. The red is left over. So that's why it's excess. The green is the limiter because it all gets used up in the reaction. It all becomes products. So this is an example of a very simple limiting reactant problem. Now, here's a picture. Here's an equation. We want to identify what's called the limiting and the excess reactants. So, before the reaction has started, this is our picture. NO, O2, NO2. If we look after the reaction, what's left over here? O2. So that means the O2 is what? Okay, the O2 is excess, and that means the what has to be the limiter? The NO has to be the limiter. So that's how one way of determining a limiting reactant if you saw a picture like this. Let's look at this picture. Same picture, different, same equation, different picture. So let's look at this here. What is the limiting reactant? Tell the person next to you which one you think is the limiting reactant and the excess reactant. All right, let's look up here. What are we thinking? What are we thinking? Limiter, which one? How many say NO is the limiter? O2 is the limiter. Okay, nobody's answering the question. Okay, other answers then?
Neither.
Neither. You say neither. How many say neither? How many say both? All right, we got both and neither. So let's see. Neither is the choice of words. Both would also work because they're both the limiter and they're both the excess. So neither of them is either of those things. Or you could say they both are. Both reactants are completely consumed. This is one of those very rare exceptions where both of them get consumed in the reaction. A perfect reaction. A stoichiometric mixture, as it's called. Stoichiometric mixture is the perfect amount according to the balanced chemical equation. This does not happen very often, but if it tells you it's a stoichiometric mixture, or if it tells you that this happens, then you know your yield is exactly what you theoretically predict, and you don't have any excess. Now, how to solve a stoichiometric problem? First of all, we know we would do what? We balance the equation. To review, then we convert the masses into what? Gotta go to moles. Determining the limiting reactant. This is the new step that you have to do in any stoichiometric problem. Then use the moles of the limiting reactant. Once you've determined which one is the limiter, use the moles of the limiting reactant and mole ratios to find the moles of the desired product. Just like we did on Friday. Convert from moles of desired product to grams usually, if we want to know grams produced in a stoichiometric reaction. And this is if you have a limiter, which you will have 99.9% of the time from now on. So we've got to know that first step. Step number 3 is what we're going to focus on today. You got to do 1 and 2 to get to 3, and then you got to be able to do 4 and 5 once you are at step number 3. So, balance the equation. Questions on that? Converting between mass and moles. Questions on that? We got those 2 skills. What about moles of a reactant finding moles of a product? What do we use to get this? Mole ratio. And then what do we use to go from moles to grams? What's up? Molecular weight or molar mass. So here, boom, balance the equation. Molar mass, limiter, and then we go mole ratio, molar mass again. Getting at it. So, We use our mole tunnel, we just have to know the limiting reactant. So, how to determine the limiting reactant? This is a sample problem. So, we have 2 of these, 9 of those, 6 of those, and 8 of those according to their equation. There's 96.03 grams of this fuel and 110.45 grams of oxygen react according to the equation above. Okay? So we've got a fuel, this happens to be propanol, and oxygen reacting to form carbon dioxide and water. So they give us this information. The first thing we have to do is determine which of those two is the limiter before we even try to get it into a product. So the first thing to do is determine the limiting reactant. That's step A. Step B would be calculate the mass in grams of carbon dioxide produced. And then the third step would be calculate the mass in grams of the reactant in excess. So this is a 3-step problem, A, B, and C. We must do A to get to B, and we must do A to get to C. So the limiting reactant is what we're going to do first. So we look at the initial amounts of reactants. There are 2 approaches to determining the limiting reactant. One is compare moles of reactants with each other and determine which one runs out first. So we compare the reactants to one another and see which one runs out first. That's approach number 1. Use that, you'll be good. Second approach, if you don't use one, you can use 2. It's an either or. Don't try to do both. It'll be a waste of time and you might mix yourself up. Number 2, compare moles of each reactant with the same product to determine which leads to the least amount of that product. So you go, okay, I got cars, I got tires. I find out how many whole cars I can make out of that. If I have 48 tires, how many cars could I make out of that? So 48 divided by 4 equals, I can make 12 cars. Or, you look at the car body. I got how many car bodies, I can make so many cars out of it. One of them will produce less total cars. So that's approach 2. Approach 1 is comparing the car body to the tires to find out which one would run out first. They're both using similar stoichiometric logic, but you can use one or the other. Let's look at number 1 first. Approach number 1. Assume one of the reactants is the limiting reactant. So you say, I'm going to assume the car body is the limiter, or I'm going to assume oxygen is the limiter, I'm going to assume the fuel is the limiter. Take an assumption and then go with that assumption. Then use the mole ratio. Calculate how many moles of the other reactant is required to completely consume your limiting reactant. So in this case, we've got 2 things. C3H7OH plus our O2 makes our CO2 plus our water. Okay? Now, don't have the balanced equation here, but as you know, the general setup is we've gotten a certain amount of grams of this, a certain amount of grams of that. Okay? So I'm assuming one of them is the limiter. You can assume either one is the limiter. So if I assume that's the limiter, okay? Assume that's the limiter. You might want to put a decimal point there or not spell it out, but that helps me remember, don't be this person. Assume one's the limiter. So you assume this one's the limiter, got to convert that into moles. Okay, moles of this stuff. Then all you have to do is convert it into moles of O2. Okay? And find out how much O2 this would be. So this is how much we have in grams. This is how much we need in moles. If the moles required is less than the moles given, okay, this would be the moles given in this case. This is the moles required. You're comparing these 2 to each other. Convert the grams to moles for oxygen, convert the grams to moles for propanol, convert it into moles of oxygen. Moles required, moles given. If the moles required is less than the moles given, then your original assumption is correct. If this is the limiter. If it's not, the opposite is true. If the moles required is greater than the moles given, like this, oh, wait a minute, I just followed the arrow. There's your limiter. If it's this way, follow the arrow. Moles given is greater than moles required. Whoop, there's my limiter. I try to keep it simple. I always assume the first one's my limiter. And I always set it up the exact same way. It makes it easy. This is just a graphic if it helps you organize your information. Although, all you've got to do is convert it into moles and compare. Okay. Now, once you have the limiter, once you figure out which one is the limiter, then you use moles of the limiter and mole ratios to determine the moles of the product or the remaining excess reactant. So once you have this done, this is just for determining the limiter. Then if you want to determine grams of CO2, okay, if this is the limiter right here, then you go whoop, convert it into moles, and moles back to grams. If this one's the winner, then what do? You take this one. Moles here, and then up to grams. Again, there's only one of those paths you have to follow. So let's look at the equation here. We want to determine the limiting reactant. So the first step is we have to convert grams into what? Convert grams into moles. So we're going to assume that our our propanol, is the limiting reactant. So we convert it into moles. 96 divided by 60.9, 1 mole is 1.598 moles of the propanol. Okay? Any questions where these numbers came from here? Yes, sir. That came from the problem here. So this is what we have in the problem. We're using this and assuming that's our limiter. So we're going to ignore that number for a second. So this is how many moles of the fuel we have. And this is how much oxygen we have in moles. Okay? So we got moles of the fuel and moles of the oxygen. Now, if this is our limiter, oh, I'm going the wrong way, that's why. I'm like, why is it disappearing? So, we're still assuming it's our limiter. Then we're converting it into propanol into moles of oxygen. So this is where we use the what ratio? Mole ratio. The 9's on top because the 9 is here. Again, I didn't write this balance, but this should be a 2 there, 2 there, 9 there. There we go. So this is where the 9 to 2 comes in. 9 over 2. If you're using the visual, this might help. This is where you're going. This is where you're coming from. 9 to 2 ratio. And that gives us 7.191 moles of O2. So I'm just going to write that down. We've got 1.598 moles of the fuel. Now, we can't compare this to anything because we haven't determined how much oxygen we started with. So now we need to compare the required and the given amounts. We required this much. We were given the 3.452. Okay, which one is bigger? The required is bigger than the given. So the required is bigger than the given. There's our greater than symbol. That means we go up, follow that. Oxygen is our limiting reactant. That's it. That's approach number 1. Okay? Approach number 1. All right. For approach number 2, you're going to pick one product. You're going to use the mole ratio and calculate how many moles of that product is formed from the given amount of the first reactant. So, okay, here's our same equation. I'm just going to pick one product just for fun. I'm going to pick this one. Doesn't matter. But just pick the same one every time. And then the first reactant is this reactant. Okay, I've got grams of this here. How many moles of that product are formed from the given amount of the first reactant? So we convert this gram into moles, this mole into moles, and then convert it into grams of CO2. All right? Leave a little space here. A little bit of space for the chemistry. Then you want to use the mole ratio, calculate how many moles of that product is formed from the given amount of the second reactant, and compare the amounts of products formed from each reactant. So we'll skip the gram step. So for our O2, we got grams of O2. We find out how many moles of O2 that's equal to, and how many moles of this it's equal to. Okay. Now we compare these two here. The moles from the first compared to the moles of the second. If the moles from the first is less than the moles from the second, then the first reactant is your limiter. And if the moles from the first reactant is greater, then we follow the path in the other direction. So it's going to be one or the other. And that would mean O2 is the limiting reactant. So basically the one that's smaller, as you go backwards, gives us the limiter. Both of these techniques work equally well. You may choose either or to make your life easier. Some people really like this one because it's the same thing every time. Okay? Some people like this because you can see certain things faster sometimes here when you're comparing the two to each other. The good thing about this is, once you figure out which one of these is the limiter, okay, let's say this was the limiter here, then all you got to do is take that, convert it into grams, and you're done if that's what the question asks. So if the question is asking, how much CO2 is produced in this reaction? Hey, once I get here, I just do one more step and I'm done. You have to do more work up front, but that's it. So how would this look? You pick one product, CO2. Okay, find out the moles of each. Same numbers as before, obviously. 3.452 here, 1.598 here. Take both of them. First one, you get 4.79. Okay? And then this should be the second reactant, because it's oxygen. Typo there. Obviously, you do the second reactant. And this is 2.3013 for this example. So you can see which one is bigger, first or second in this case. Okay? So the first one is bigger. That means the second one is our limiter. So, just like before, O2 is going to be the limiter. We didn't change the problem at all, so we expect the same results. And from that, we could determine, if we wanted to, the grams of CO2. So, step B, calculate the mass in grams of the CO2 produced. Once we find the moles of the CO2, which is 2.3013, we then multiply by the molar mass of the CO2 here. Molar mass of CO2 there, and you get 101.28 grams of carbon dioxide produced in the reaction. So that would give you the amount of CO2 produced. In the last step, after we get the product, step C asks to calculate the mass in grams of the reactant in excess. So which one was in excess? The fuel or the oxygen? Fuel was. So the fuel is in excess. Excess means it's extra. The oxygen in both cases was the limiter. So what you can do here is you just convert the moles of oxygen that you have. It limits the reaction. And you find out how many moles of the fuel you would need in order for this to work out. So in this case, you do 3.452. You're converting backwards from this to this. So you're going 2 over 9. 2 over 9 gives you 0.7671 moles. Then, to get to grams of this, you take the moles of this times the molar mass. You get 46.10 grams of C3H7OH will be used up. That's how much will be used up by the oxygen. And then you just take the original mass, which was 96.03, minus the stuff that gets used up. And you got 49.93 grams left over. So that's just finding out how much you have left over of the fuel. So that's to calculate the excess in a given stoichiometry problem. So those are the steps. Finding the limiter is the first and most important step, and once you get through that, you can do the excess or the product for those steps. Now, another way to approach a problem is what is called an ICF table. So, I would like you to draw this out, everybody to draw it out. It's another way of approaching a problem that can be extremely helpful here. So, when you have an equation here, if you draw a table right underneath the equation, the I stands for initial. The C stands for change. So you write down your initial conditions, you write down what changes. And the F stands for final. So at the end of the reaction, what you end up with. Now, this says that 3.452 moles of O2 is the limiting reactant. All of these have to be in moles in order to use the ICF table. You've got to be counting in moles only when you use this table. Now, the initial amount here, you had 3.452 initially of O2. The 1.598, that came from our molar mass of the our amount of C3H7OH. It's 1.598. That's from up here, as we saw earlier. So you write down the initial amount. So the first thing you do is convert to moles, write down what you start with. In the beginning, there are no products. 0 CO2, 0 H2O. No products in this reaction. Then you find out how much does it change in moles. So what's going to happen is your reactants, some of them are going to turn into products. How much is going to turn into products? Your limiter is the change. Your limiter gets completely what? Completely used up in the process. So you expect at the end, the final, your limiter is going to equal 0. So you lose 3.452 moles of O2. This reactant turns into a product. Then do you lose 3.452 of the first reactant? No, because the ratio is not 1 to 1. It's 2 to 9. So instead of being 3.452, it's 2/9 of that. And there's our mole ratio in our ICF table. Then we've got what we're losing from the reactant side, which is becoming a product. Now for CO2, we've got the same situation. If we've got 3.452s of this, 6/9 equals how many moles of CO2? 6/9 of 3.452 is gained. And what's going to be the fraction in front of the water? 8/9 times 3.452 again. So this makes it a little easier to notice and to see how things are changing. Okay? How things are changing. So when we calculate this out, we can see that we've got 1.598 to begin with. We lose this much of it. Here, we lose all of it. Here, we gain some, and here we gain some. Again, those are the changes in decimal form. So 1.598 minus 0.767 equals 0.831. That's how much is left over of our fuel. Should there be any of our oxygen left over? No, definitely not. This should be negative 3.452. That shouldn't be 0 there yet. So we gain 301 moles of carbon dioxide and 3.068 moles of H2O. The nice thing about setting up a table like this is, if they ask you how many grams of H2O are produced, all you have to do is take this number and multiply it by water's molar mass. If they ask how many grams of carbon dioxide are produced, take this number, multiply by the molar mass. If they ask you how much is left over of this fuel, you take this number and multiply by its what? Molar mass. All you got to do. ICF table keeps everything organized and neat. I personally am not a fan of fractions. That's just my personal. I always do decimals. But the fractions can show you where the things come from the mole ratios. Sometimes it's easier. If the problem's not asking for this, you can stop and you don't have to complete that portion. Okay? But this is when you have a limiter, and then this is excess here. So this is how to use a ICF table to calculate not only the limiter, but also what is being produced and what is in excess. So here's our excess reactant, here's our moles of first product, here's our moles of second product, and then our moles of the limiter obviously is 0 at that point. So that gives us almost any answer we want in one table. Now, when we are trying to calculate amounts, one way of doing this is called a percent yield. A percent yield measures the effectiveness of a reaction procedure. So if everything works out perfect, you would get 100% yield. Every single reaction becomes products. But in reality, these molecules are trying to collide together. As these molecules are trying to collide together, there are some that do not collide together to form a product. This is what is called an actual yield. Some of them will not. Theoretical yield is the amount of product that would result if all the limiting reactant reacted. If all the limiting reagent reacted. The actual yield is the amount of product actually obtained from a reaction. So today when we do our lab, as we are doing our lab today, we're going to be able to see, well, how much is actually yielded, how much is produced in the reaction. This is usually from an experiment, or it's given to you if you didn't do the experiment, if it's like on an AP test. Theoretical yield is what you calculate, and percent yield is a calculation comparing these two. This is the formula for percent yield, and it's an important one. Double red star. It's one of my favorites because after you do all the stoichiometry work, this is like, oh yeah, you stick the actual over what I calculated. Times 100, of course. And this gives you a nice number that usually is less than 100%, not always though. We'll learn about, well, how can you get over 100%? There's some unique things that happen in the lab. Now, in some college chemistry classes, you are graded in the lab based on your percent yield. So they go, hey, make this. You got 6 hours. Give them 6 hours. Your percent yield isn't high enough. They say, get 0. Or they say, explain why you didn't do it and write a new procedure, next week come back. But depending on the lab. Percent yield, for us in here, we will be using this to evaluate our procedures and to evaluate how much we produce in a reaction. The more you can produce in a reaction, again, closer to 100%, the better the reaction is. The more efficient the reaction is, there's a lot of benefits when you're producing certain products. Now, percent yield implications. It is nearly impossible to achieve 100%. Nearly impossible. However, correct procedures will almost always achieve less than 100% yield. Correct procedures. If you do everything right, you get less than 100%. That's good. Why is that? First of all, there are limitations in measurement accuracy. So we're limited by the measurements we're making and the accuracy of those measurements, the equipment we're using. The next thing is the reaction does not go to completion. If the limiting reactant is not completely consumed or is not able to be completely consumed, you can have some limiting reactant left over at the end that does not react, or the reaction achieves a state of equilibrium, where it's not only going forward, but it's also going in reverse. And that causes you'd have a less than 100% yield. The other thing that could happen is additional reactions can occur. You can have different reactions occurring that were not supposed to react, or side reactions that occur between the chemicals in the system. Now, there's also the case where you get over 100%. You're like, yeah, I got 110%. All right, give all you got. Unfortunately, when you write down 110%, you're going to go, oh boy, what happened? You want to explain what happened. Less than 100%, these are some things that could happen. More than 100%, what could happen? Usually the product is impure. It's a combination of a few different things. Maybe there's another reaction that occurs. Maybe there's something left in the product that it's not supposed to be there, or that came out of somewhere else, or out of other chemicals that you were adding that you thought was not supposed to be there as well. So the product is impure. There is contamination. That's usually the number one thing for over 100% yield. That contamination adds mass to it, adds moles to it, and that puts you over the theoretical yield. Your actual yield is on over what the theoretical yield should be. So these are some good reasons, and when we calculate our theoretical yield in the lab, you're going to have to explain what happens and why. Regardless if yours is over 100 or less than 100, you got to explain why. If you get exactly 100, you still have to explain why. You're like, oh, it's not perfect. Well, 100% yield is very, very rare. So, not perfect, but I got contamination. Okay. Not about you, it's about the chemistry. Any questions on theoretical yield and percent yield and actual yield? So our stoichiometric calculation is our theoretical yield. Our actual yield is what is done in the laboratory, or done in somebody else's laboratory, depending on where you get the data from. And then we have implications for our percent yield, what it means. Now for percent yield calculations. Okay, if a student reports a yield of 82.34%, we can calculate the mass of CO2 collected by this student. So we've got these amounts here, same amount as before, so 82.34%, we can use our percent yield calculation. Okay? If the theoretical yield is 2.3013 moles, or 101.28 grams, we put the 101.28 on the bottom, 82.34% here. Our unknown is our actual yield, which we put in as X in this case. And we can calculate out that this person collected 83.39 grams of CO2. Yes?
This is theoretical yield from the part of the problem that you did before.
Correct. Yep, theoretical yield, same problem. This is part D of the same exact problem. Okay, so we're not changing any of the numbers or equations. So usually the easiest way is to convert this into moles, and moles into grams, and use the grams over grams. You could also do actual yield in moles, but then you have to convert to grams at the end anyways. So using this equation, you can solve for percent yield if you have these two, or you can solve for one of these two if you have the other ones. So could you be given actual yield and percent yield? Yes, you could. You'd say, what's the theoretical yield? That would be another way of approaching it if you weren't given those things. But this is a common way of using the same type of problem in this order. This is a very common thing to use percent yield as. How to use it. Now, if we look at this reaction, let's look at the steps and just follow along as we look at the steps. You don't have to write this down step by step. According to the reaction above, we have 124 grams of Al are reacted with 601 grams of Fe2O3. So, to identify the limiting reactant, that's the first step. Calculate the mass of each product formed. And then, if only 53.1 grams, that's the actual yield, we would find the percent yield. So, A, for the limiting reactant. Okay, convert grams of aluminum into moles of aluminum. Then convert grams of iron, Fe2O3, into moles of iron of Fe2O3. Then convert moles of aluminum into moles of Fe2O3 needed, and compare the two. So how would this look? Okay, here's our aluminums converting into moles of aluminum. Iron compound into moles of iron. And then aluminum into iron compound. We compare these two, which one is bigger? Okay, the iron compound that we originally have. Okay, so the moles we given is bigger. That means that the other compound, the aluminum, is going to be our limiting reactant. Okay, same process. Now we have the aluminum as the limiting reactant. We've gotten that. Step B, calculate the mass of each product formed. So we use our moles of aluminum, convert it into moles of aluminum oxide, then grams of aluminum oxide. Then moles of aluminum into moles of iron, then grams of iron. So those are the steps. Solution here, you go moles to grams. And there's our moles to grams of the iron. This is showing all the steps, all the calculations. Sometimes you can just draw out a map with arrows showing where you're going, and then you just step by step go through it. Multiple step problem, you've got grams of one product, grams of the other product. That's B. Now, if only 53.1 grams of Fe is recovered, so we just want Fe. If only 53.1, theoretically you should get 256.7. So what do you put on top? 53.1 over 256.7 times 100, percent yield 20.7%. That's it. C is usually the easiest. A is usually the most work, and then once you get that work done, everything else, just keep going with that. So that's percent yield. So if we look at this reaction here, okay, if we started out with a ratio of 4 NOs to 4 O2s, there we go, open it up. Oh, open. Open my door. The bottom switch is a switch there. All right. So we'll get back to this animation in just a moment of what is happening. Yeah, the limiting reactant is the one that, again, the one that does not get used up, so it should be found at the end. So if we look at these here, what's left over? O2, NO, or NO2? O2, there's an O2 floating around on each side there. So as you can see, it depends on, again, depends on the amount.